I will share the link again.
Okay, welcome everybody to a new session of our differential geometry webinar, AmSur-AmSul. For us, it is a pleasure to have today as the speaker Viviana del Barco from Unicamp, and she will talk to us today about G2 instantons on nilpotent Lie groups. As usual, you will see the announcements on the chat about how to join our WhatsApp group or the mailing list. Okay, well, thank you, Viviana. Go ahead, please.
Okay, thank you, Adrian, and thank you to the organizers. It's a pleasure to be here and see so many friendly faces. I just sent the link of just a bit before of the announcement of the slides, in case you want to go forward or backwards. I usually have that kind of desire when I watch a talk. So please feel free to interrupt if you have any question or comment. And today I will present G2 instantons on nilpotent Lie groups. This is something that we've been working with Clarke from Rio de Janeiro and Andrés Moreno from Unicamp. And the idea was to try to build more G2 instantons, which I'm going to say now, using some techniques of a previous work with Alberto Rafero and Andrés Moreno, that we worked with G2 structures and nilpotent algebras as well, or Lie groups. So okay. Oh, it's not working. Okay. So this is the outline of the talk. Oh, sorry. This is the handout version. So usually something is not working. Wait, I have to. Sorry, apologize. I will share now. What is this? Okay, do you see the screen now? Yeah. Okay, so this is the outline. First of all, I will give some preliminaries on G2 structures and what a G2 instanton is. Then I will go right away to the results, explain, the preliminaries will also contain which is our setup and where we are looking for G2 instantons. And then I will show you what we managed to obtain in this setup. And then I will go, so first I will present the results without giving any proof. And then I will not give any proof either, but I will give some ideas on how we managed to prove the results. The results, if you go on the preprint, you will see that there are a lot of computations because they involve curvature and it's not easy to handle. So much of the work was to try to put things in a nice basis or in a basis that is suitable both for the G2 structure and the algebra structure, as I will say later. So I will tell a little bit about the technicalities, but I will not give either any proof. And if I have time, I will mention some applications that we are working with other collaborators. Okay, so everything is based on this paper. And if you have the slides, you can, here you cannot, but you can click on the link of the archive. So let's start with the preliminaries. So, okay, I have to start with the definition of a G2 structure. So I will work with 7-dimensional, M would be a 7-dimensional manifold. And I would say that a G2 structure on the manifold is a differentiable 3 form, such that at any point satisfies this non-degeneracy condition. And any such 3 form will define a Riemannian metric on the manifold and an orientation via this Barco. Okay, so point-wise, when you have a G2 structure on a manifold, at any point you can find the basis of the tangent space where the G2 structure has this form, and the Hodge dual is given by the other form, okay, of the Hodge dual of the 3 form. And let me say, of course, for those who are not familiar, EIJK denotes EI, which J, which EK. Okay. So this is the setup. We have a manifold and a G2 structure. And if we denote with nabla the Levi-Twitter connection, then Fernandez and Ray, they showed that the G2 structure is parallel with respect to the Levi-Twitter connection, if and only if the structure is closed and closed. So I think that what they proved is actually this, if and only if. And it is known that when the G2 structure is parallel, then there is a reduction of the holonomy of the Riemannian manifold. Okay? This, well, of course, holonomies with manifolds, manifolds with holonomy G2 were an object of study ever since the Berger list. So to construct them, so it was very active, and it is nowadays very active subject. But this characterization, well, the G2 structures which are parallel with respect to the Levi-Twitter connection are called torsion-free, and in this case, the manifold is Ricci-flat. But I wanted to mention this characterization because this second term gave rise to other, well, and other studies as well. They gave rise to less restrictive conditions than parallel that can be considered on the 3 form. Okay, so I may have a G2 structure which is not parallel, but it can be closed or closed or satisfy other equations. So this gave rise to other G2 structures which gained a name. Of course, a G2 structure is called closed if the 3 form is closed. It is coclosed if the Hodge dual of the 3 form is closed. It is purely coclosed if it satisfies these 2 equations, and it is nearly parallel if it satisfies the last equation. And let me say that in this talk, I will concentrate on these 2, and and for those who are familiar with the torsion forms, these are the torsion forms that correspond. I will not get into detail with that. But let me say, as you can see, every purely coclosed G2 structure is coclosed. Okay, so I would say that the class of PCC is contained in coclosed. Okay, because I will be working with those. Not every manifold admits a G2 structure, but for instance, in the compact case, if it admits if a compact manifold admits a G2 structure, then it admits a coclosed G2 structure. So in general, coclosed G2 structures are something abundant in the set of manifolds, in the category of manifolds, let's say. But coclosed is more difficult. But just, yes.
One question. This last condition, nearly parallel, means that the 3 form phi is a killing form?
Exactly.
Okay.
Exactly. It is exactly that. The 3 form is a killing form. Yeah, I wrote it like that exactly, because there is another characterization there.
And there are many examples of that?
They are classified in the homogeneous case,
Okay.
as I know. Like Kath, Moreno, Friedrich, and Baum, I think.
Okay, thank you.
Well, not in Lie groups. I've learned that not in Lie groups, not unsolvable Lie groups. These manifolds are always Einstein with positive scalar curvature.
Okay.
Okay. So, okay, I wanted to mention that purely coclosed is inside coclosed. It's a subclass of coclosed. And there are, of course, a lot of other classes that I will not mention, but they are also considered. Okay. So let me say that any G2 structure on a manifold induces a decomposition of the bundle of forms, of K forms. And in particular, I will be interested mostly in the decomposition of the space of 2 forms on the manifold, which decomposes as a 7-dimensional summand and a 14-dimensional summand. And the 14-dimensional one is characterized by being the set of 2 forms whose wedge with the dual of the 3 form is 0. Okay, so this is the kernel of an operator, and actually is isomorphic to the Lie algebra G2. Of course, yeah. But okay. So within the context of G2 structures or manifolds, there are some objects which are called G2 instantons. If you have a differentiable manifold and a G2 structure, then a G2 instanton is a connection on a vector bundle over the manifold such that the curvature satisfies this equation. So let me say that here, what we are considering is that nabla, you can see it as a pointwise, at least the connection on the bundle, you can see it as a matrix of 1 forms, and the curvature can be seen as a matrix of 2 forms. I will show some examples later. I was not used to work in this way with these characterizations of connections and curvatures, but I've learned to do these computations, and it's much easier. So here, the curvature represents a matrix of whose entries are 2 forms, and what we are requiring actually is that each 2 form of the matrix is inside this lambda 214 that I mentioned before, because we are requesting that the wedge of the Hodge dual of the 3 form is 0. Okay, so this is what a G2 instanton is a connection such that the curvature is, let's say, in this omega 214 is in G2, okay, because omega 214 was isomorphic to G2. Okay, so this is a definition. At some point, it became of interest. I'm not a specialist at all, but at some point, it became of interest, mostly first in the case of torsion-free G2 structures, in order to study the moduli space of torsion-free G2 structures on a manifold. Okay, but then there became online some examples of G2 instantons over torsion-free G2 manifolds. That is manifolds with autonomy T2, but then they started to be constructed, the G2 instantons, on manifolds having closed, coclosed, or other kind of torsion G2 structures. Okay. Nowadays, well, it's plenty of literature. I will say that I will only give some references. All the references are in the article, or I can send it to you, but everything is in the article, as far as I recall. But also there was a physical interest due to Strominger systems or heterotic G2 systems. What is an heterotic G2 system over a G2 manifold? Well, first, we consider, and before you read that, I want to make a disclaimer. I will only give a definition that fits in my framework, okay? So the definition of G2 system or heterotic G2 system is given in the more general way with three forms coming from other contexts, and the G2 structure may not be coclosed. I will require it to be coclosed, but I will give just the setting in this framework, okay? Don't take it as the usual definition. Okay, so an heterotic G2 system with phi being coclosed is a pair of connections, A on a vector bundle and nabla on the tangent bundle of the manifold, such that they verify these equations. So we have, you can see here, we have the instanton equation for nabla, the instanton equation for A, and you have what is called the Bianchi identity, which requires here a difference of trace being equal to the differential of T, where T is a three form defined via the G2 structure. Okay, these are the T actually comes from the torsion of the G2 structure. Okay, so this is what is called a heterotic G2 system. As you can see, of course, G2 instantons are the base of solutions of heterotic G2 system. Actually, you need two instantons and this equation to be satisfied. Let me say that here what we are doing is, as I said, R lambda can be considered as a matrix of two form. So you make the wedge product of matrices of two forms that gives you a matrix of four forms, and then you take a trace, and that has to be the differential of this T, which is a four form as well. Okay. And here we require alpha to be positive. This is also an issue of discussion if it's positive or negative, but there are some physical motivations that I will not get into that because I also am not an expert. Okay. So this is more or less the motivation. Let me see where I'm going. It is not clear in general, of course, if you have a manifold with a G2 structure, which connections nabla or A should be or could define an instanton on your manifold with a G2 structure. That depends on the manifold, depends also on the G2 structure. You may have instantons that work for a G2 structure but not with others, etc. When phi is coclosed, and that's why I gave this condition, when phi is coclosed, there is a natural connection nabla, which is to choose, which is the characteristic connection, which is introduced by Friedrich and Ivanov in 02, and is defined by the Levi-Civita connection, and this having this torsion T, where the torsion is the one I defined before. I just recopied here, and satisfies that phi is parallel with respect to nabla 1. So actually what Friedrich and Ivanov showed is that when the G2 structure is closed, there is a unique connection with the skew-symmetric torsion such that the three form is parallel. And they gave exactly the formula, and they said this is the one. Actually, the result is proved for conformally coclosed, I think, if I'm not wrong, but it's a class which is larger than coclosed. But since we are in the coclosed setting, I will again state things for coclosed. Okay, so for when you have a coclosed G2 structure, you can define this connection, and this connection was proved to be a G2 instanton for nearly parallel structures, which are also a subclass of coclosed. Okay, and this was shown by Harlan and Knoll in 2012. So this is the connection that we are going to work with, and we wanted to give some more generality. So instead of having a 1/2 of the torsion, we just included the parameter here, lambda. And the question that motivates our research is we want to determine when this is a G2 instanton for phi coclosed. for phi coclosed. So here, how and no, they prove it for nearly parallel, which is a subclass of coclosed. We want to show it in the larger class coclosed. Of course, this problem is completely, well, it's way more difficult. As I said, nearly parallel structures were classified. I'm not sure of the method, so I'm not going to say much. But it's a small class, and for coclosed, well, it's significantly bigger. So we want to do that, but of course we need to restrict ourselves to a smaller class of manifolds. So this is where Lie groups come into the picture. So yeah, and myself. So we are going to work in the manifold context. So this means that we are going to restrict ourselves to this context. So for me, M will be a simply connected nilpotent group of dimension 7. Phi is a left-invariant G2 structure. That means that it's preserved by left translations. And in this setting, remember that when you have phi, you compute T. Then since phi is left invariant, T would be left invariant, and nabla is coming, the metric is also left invariant. In this case, the induced metric by the G2 structure is left invariant. So the connection, this connection is left invariant in the sense that left translations are affine transformations of the connection. Okay, so this means that we are able to work at the Lie algebra level. But before going to the Lie algebra, I want to say that when you work with G2 structures and G2 instantons, which are left invariant, then they are potentially induced to compact quotients, which means the following: if the nilpotent group has a lattice, then the G2 structure and the G2 instanton descend to a compact manifold, which is the quotient of the Lie group by a lattice. So I will mention a list of non-exhaustive interesting results that will be around the talk. So first of all, let me say that there is a lot of, well, some people studied left-invariant coclosed G2 structures or nilpotent groups. Bagaglini, Fernandez, and Fino, they started with, as far as I recall, is for two-step nilpotent. They worked through the classification of 7-dimensional two-step nilpotent, but they also have examples on 3-step nilpotent. And they sort of classified the algebras that admitted coclosed G2 structure. In 2022, we took another approach, but we also studied coclosed and purely coclosed G2 structure on two-step nilpotent Lie groups. And actually, since we didn't go through the classification, there are tools that we are going to use in this, that we used actually in this paper. And in 2023, there is a classification that grows, of course, in dimension 7, but has nilpotent Lie algebras of nilpotency step larger than 3. I think they go up to 4 and classify which ones have purely coclosed G2 structures. But Bazzoni, Garvin, Munoz, they also rely on classifications of the algebras. And what about left-invariant G2 instantons? What was previously known on nilpotent Lie groups? We were not the first ones. There is a paper of Ivanov and Ivanov in 05 where they construct, in general, for SQ3 structures, they construct, G2 instantons starting from SU3 structures of a certain type, and they give examples on nilpotent Lie algebras or Lie groups. And they give an example of a two-step nilpotent Lie algebra, which will appear here, but it's not the same of ours. I will mention that later. And then the starting point actually was also a paper of Fernandez, Ivanov, Villacampa, and Ugarte, 2011. They get a G2 instanton, and actually they propose solutions for the atherotic G2 system on the Heisenberg Lie algebra of dimension 7 and the 5-1 cross R2. So those works are very due to instanton. And the last one, I want to mention it, even though it's naturally reductive. At some point, they get the quaternionic Heisenberg. They were classifying naturally reductive spaces. The quaternionic Heisenberg appears here, and they say that the canonical connection of the naturally reductive space is the connection of Ivanov defined by a certain digit structure, and they do some computations which of the holonomy and so on, which you can deduce from there that the connection of the natural reductive space is actually a G2 instanton, but it's not mentioned there. We discovered there that later. So sort of you can deduce that, but it's not if you join like the dots. Okay. So from the Lie algebra perspective, I will explain a little bit of the setting in the Lie algebra perspective. You know that when you take every structure to be left-invariant on a Lie group, then everything reduces to the Lie algebra. So I will denote with N the Lie algebra of the Lie group, and my G2 structure, which is left-invariant, will become a 3-form on the Lie algebra. And it will induce an inner product in the Lie algebra as well. So just as I said at the beginning, I can take an orthonormal basis of the Lie algebra such that the 3-form is that, and the dual form is the following 4-form. And I would say, let me just say now that I would call, if I have an orthonormal basis, I would call this phi the standard one. Okay, so if I have an orthonormal basis, this phi will be the standard one, and let me mention that we have the term 5, 6, 7. In case some people is used to work with other conventions of G2. So not conventions, just the G2 form. Okay, so we have a Lie algebra. We take an orthonormal basis, and we know that the G2 structure will have there is an orthonormal basis such that the G2 structure has that form. And the Lie algebra structure is encoded on the differentials of the dual base of the Lie algebra. Okay, and these are what I call alpha i's, which are 2 forms of the Lie algebra. And this, let me say that this differential is the same as having the Lie bracket. Okay, so it's the dual of the Lie bracket. So all the algebra structure is encoded in the differential. So once you have the 3-form and the differential, you can compute the torsion form of the G2 structure very easily, let's say. And then once you have the torsion, you define your connection, the Ivanov and Friedrich connection, which is for us an operator from N to N to N. And you can compute the curvature and, well, you can compute the curvature, which will be denoted by R lambda of this connection. And then, okay, the question that we want to answer is for which set of 7 2-forms, remember that these are the differentials, will this equation hold? So this procedure actually, or this kind of question can be, of course, done on any Lie algebra, not, well, I'm not using nilpotent here, but of course that this problem algebraically is not doable at all. I mean, maybe by computer, but I don't think. I mean, your unknowns are 7 2-forms on a 7-dimensional Lie algebra. So, and you have to compute the torsion, which of course is we'll have you have here well, have the curvature. So in general, it's not doable. So what we did is, just now the results. What we did is to reduce, here I'm working on any algebra and on nilpotent group. So the results that we obtain are on two-step nilpotent groups, but even there is not that easy. But let me tell you what we did to follow this, to try to answer this question. So we assume that the algebra is two-step. That means that the commutator, which will be denoted by n prime, is contained on the center of the algebra. Okay, this means two-step, and also the commutator is non-trivial, so the algebra is not abelian. On the one hand, once we have a two-step nilpotent algebra, we can decompose the algebra. Of course, we have we are carrying here a three form, and which induces an inner product. So I have n prime, and I consider the orthogonal complement. I can decompose the algebra and then the dual of the algebra, which can be seen as this orthogonal decomposition as well. And I have the differential here. The differential will behave differently in these two terms. Actually, it verifies the following. The differential restricted to the complement of n prime is 0, and on n prime, on the dual of n prime, is injective. In particular, since the algebra is 7-dimensional, that tells you that the dimension of n prime is always less than or equal to 3. But on the other hand, I have a G2 structure there, so I will have an orthonormal basis such that the 3 form will have this standard form, as I said before. The problem is that, in general, this basis is not adapted to this decomposition. Okay, we would like to be adapted so that the G2 structure and the algebra structure are compatible in some sense, so that makes the computation of the differentials and the computations of the torsion, of the curvature, and so on, and the instanton equation to be solvable or to be attainable, treatable. So we ask ourselves, how can we get through this issue? And this is what we do. We change the G2 structure, the given G2 structure, by an equivalent one. Let's say by a G2 equivalent. Well, actually, I think I wrote it wrong. Well, let's say, I would say, what do we do? What we do is we act on the algebra by an element on G2, which preserves the G2 structure and changes the algebra structure. Let's say, we act on the G2, because the G2 structure, since we act by an element of G2, then we preserve the G2 structure, but we change the basis so that the differentials are nicer. Okay. So I think I wrote it in a strange way. So, and then, of course, we start with that, and then we make a lot of computations in a very smart way. Well, the way that we were able to do it. So let me tell you the results. What we got. So we proved that if the connection, depending on one parameter, is a G2 instanton, then the parameter is 1. So, and we prove it, we prove this for any two-step nilpotent algebra, okay? So let n be a two-step nilpotent algebra, and phi coclosed. And nabla lambda is nabla g plus lambda over 2 times t. So if this connection is a G2 instanton, then lambda needs to be 1. So that means That means that in this family that we consider, actually the only possible candidate is the characteristic connection, the one by Friedrich and Ivanov. Okay. And the main theorem that we got, which is the following, which is a complete characterization. We say that for a nilpotent algebra, there exists a coclosed G2 structure for which the characteristic connection, which is the only candidate, is a G2 instanton if and only if the Lie algebra has a basis such that the structure of the Lie algebra is the following. And here we give 3 families of Lie algebras. I will get into detail in a moment. And in this case, the G2 structure is the standard, let's say, of this basis. We also know that in the first case, the G2 structure, the one given, the standard one of this basis, is purely coclosed, has to be purely coclosed. And in the second and the third, it is not purely coclosed. So it is coclosed, but it cannot be purely coclosed to be an instanton. Okay. So as you see, we were able, again, let n be two-step, and yeah, two-step nilpotent. So we kind of solved the problem for the characteristic connection on two-step nilpotent algebras. So this is a classification. And let me say that the first ones were the G2 instantons considered by Fernandez, Ivanov, Ugarte, Villacampa. So they were known. The second one, this is the quaternionic Heisenberg, and these were the ones that appeared in Agricola Ferreira Storm in the context of naturally reductive spaces. And the third one, as Lie algebras, they are the same as the Ivanov, but the G2 structure is different because ours is coclosed, and the Ivanov example is not coclosed. It has more torsion, well, different torsion. So, in principle, as far as we know, this is a new instanton, let's say pure new. The second we kind of included in the classification, and the first one was for sure very known. So, question?
Yeah, a quick question. I missed my connection a little bit. Don't know if you mentioned it. So the proposition that is just above, is it just for two-step nilpotent, or is it
for two-step?
Two-step, right? We don't know in general.
No, we don't know.
Okay.
No, we don't know.
All right. Okay.
Yeah. Thanks. Any other question or comment you want? I will not have time to say anything. Okay. So at least you know the results. And okay. So let me say the results put in a different way. A two-step nilpotent algebra admits a coclosed G2 structure such that the characteristic connection is a G2 instanton if and only if the algebra is either R2 times H5. This is the Heisenberg of dimension 5. H7, which is the usual Heisenberg of dimension 7. The quaternionic Heisenberg, and the last one, which is this 6-dimensional the algebra plus an abelian ideal. This N32 is the two-step nilpotent algebra, free two-step nilpotent algebra, so nilpotent algebra on 3 generators. And from a geometric point of view, I want to say that this property that Agricola, Ferreira, and Storm showed for the second case actually holds for all the instantons that we have, because if we show that if Napla 1 is a G2 instanton for a coclosed G2 structure on, of course, n two-step, and the G2 structure being left-invariant, then the Riemannian manifold is naturally reductive. Okay, so if you have if the characteristic connection is an instanton, then the space is naturally reductive, and actually the characteristic connection is the connection of the naturally reductive, is the canonical connection of the naturally reductive space. And the converse is not true, because there is this Lie algebra, which is the usual Heisenberg of dimension 3 times R4. This is naturally reductive, but the number one is not an instanton, because we need the G2 structure to be purely coclosed. We proved that, and this Lie algebra does not admit any purely coclosed, and we proved that with Moreno and Rafael previously. Okay. Okay, so these are the results at a large scale. Let me give you an example. So I will only mention, well, here I will only describe with a bit more of detail the third case, okay? This one dimension, the 6-dimensional plus 1. So let me explain that. So M is the algebra having this basis where the differential of the first 4 elements is 0, and the differential 5, 6, and 7 is this. And we consider the standard G2 form on this basis. So from here, from the differentials on the 3 form, you can compute the torsion, and the Levi-Civita connection is easily doable. So you can compute nabla 1 as and you can express it as a matrix of 1 forms, which is a matrix of size 7 by 7, and this is a block diagonal matrix, and in the diagonal you have a 0, then this 3 by 3 matrix, and then this 3 by 3. Okay, this is a matrix of 1 forms, and you can compute the curvature, which is a matrix of 2 forms, and these are the non-zero entries of the matrix of 2 forms, which are these ones. Okay, and from here you just take for each of these components, you take the wedge with the Hodge dual of the 3 form, and you can readily check that this is 0. Okay, so it is an instanton, and you can also compute the usually instanton condition does not give you allonomy in G2, but in this case it gives you that the allonomy is SO3, which fits inside G2 inside SO7. Okay. In the other examples, you can also make in the preprint we have the 3 examples made with all the computations, even the one that was previously made by Fernandez, Ivanov, and these people. Okay. Okay, so these are the results. Good that I scaled it like that. So I will only mention technicalities. Yes.
So before you go into the technicalities, just I think I lost track of the Bianchi identity, right? The heterotic Bianchi identity. Where did you drop that? I mean, or is it automatically satisfied by these guys?
Okay, so I will take. I promise I didn't organize it with Enrique. He's not here, but. So since you ask, I will go to the 4 and then I come back, because I will not have time to go to technicalities. So I didn't mention anything about the solution of the heterotic G2 system, but since you ask, I will go to the 4, not that far. So these are the applications. So as you see, as I just told you, we got some examples. We got one or two parameter families of the algebras and G2 structures that are instantons. So the motivations I told you were to find solutions of the heterotic G2 system. And this is something we didn't do in the paper with Andrew and Andrés, but we started to discuss with Andrés Moreno and Rudolf Holder after we finished. So, and actually remember what an heterotic G2 system is. I just copied what I put before. You have a G2 structure and you have 2 connections in the bundle. You have 2 bundles and 2 connections, which are both instanton, and this is what Enrique was asking, the Bianchi identity. Okay,
Yeah.
so what we did is in our examples. So let me just mention what we did in our examples. We just found a nabla, which is a G2 instanton, so that will fit here and here, the R, the curvature, and we just took A equal, you can just take A equal to 0, okay, if it works. So what we did in the examples appearing in the main theorem, so for Lie algebras 2 and 3, actually, because for the first Lie algebra was already done, but for the first two, well, for all of 3, we have that it verifies the instanton equation, and one can check that the differential of the torsion actually gives you exactly this term, okay, for alpha positive. Actually, you can compute alpha, and these are the values depending on the case. So this tells you that our G2 instantons, you can take A equal to 0, and then the Bianchi, well, of course that it is an instanton, but also the Bianchi identity is satisfied because of this. And these 3 families in the main theorem give you solutions of the heterotic G2 system on compact manifolds, because this, well, within this family you can always, you can have lattices there. So this gives you solutions on compact manifolds as well. Okay, so I didn't mention it before. This is something we are working now, and actually it is possible. These connections. This is the characteristic connection I was just talking, and it is possible to also define connections which are not in the tangent bundle. So in these examples, we have a connection on Tm, and we have A equal to 0. But we were working, and you can have a connection on, oh, it's not equal, a connection on E, and then you can take nabla equal to 0, and we have those examples as well. But this is ongoing work. Okay.
Thank you.
So you're welcome. If I may, I will go back to technicalities a little bit. So, as I say, I will go into details of the proofs, and well, this is the thing I wrote a bit strange. Yeah, I don't know. But okay, what the idea is to go into details on how do we did we manage to do these calculations? Okay, because calculating, I mean, we always have the G2 structure like fixed like this canonical, the standard G2 structure on a basis of the Lie algebra, but then we need to find what our unknowns are, the Lie algebra structure for the curvature to satisfy the G2 condition, the G2 instant condition. So as I say, well, the tools will depend on the dimension of n prime. And in both cases, we build on previous results obtained by Moreno, Raffero, and myself last year. Well, a few years ago, published last year. So let me first say a few words about n prime dimension equal to 1. We have then we consider coclosed G2 structure on a Lie algebra. N prime has dimension 1, so you can split your Lie algebra as this, as I said before. Then the G2, there is for the G2 structure there is an orthogonal basis such that phi is on the standard form. But since G2 acts transitively on the sphere, we can assume that E7, so we take E7, assume that E7, the last vector of the base, spans n prime, because because we take an element of n prime, we use this transitivity. The G2 structure is preserved because we are acting with an element of G2, but we changed the basis, so we changed the differential. Well, not the differential, the basis to which we can compute the differential. So that means that we are able to make differential of EI to be 0 for I from 1 to 6, because here n prime is the only one that has differential for the Lie algebra. Then, as usual, we use, since the complement is 6-dimensional, then we write everything in terms of an SU3 structure on the 6-dimensional piece. Here I'm naming J, the complex structure of the SU3 structure. And this is something we also proved with Moreno and Raffaello, that if it is closed, then J needs to commute with this operator. Here I'm taking, that D of E7 is in lambda 2 of the complement of the dual of the complement, and I am using this isomorphism with a skew-symmetric maps. Okay, for those who are familiar, this is minus the JZ map. Okay, but I will not mention the JZ. So what we know is that J needs to commute with this skew-symmetric matrix. So in some sense, we can diagonalize them in a generalized way together. And then we can find a basis of the Lie algebra, well, of the complement now, such that the differential has this form. So it's a multiple of 1, 2, 3, 4, 6, 7, and 5 is the standard one, is the usual G2 structure. So that helps us a lot in the computations. And once we have this very adapted basis to both the G2 structure and the Lie algebra structure, we are able to compute everything we need. This term, then the torsion, then nabla, of which of course is a matrix of 1 forms, which is already very complicated, and the curvature very complicated. And what we did in this case, we proved, so in this n prime equal to 1, we proved that the connection is an instanton if and only if lambda equals to 1, as I told you, and a plus b plus c is 0. And notice that this condition, actually, because of this, tells you that the G2 structure is purely coclosed. Okay, so this means that the G2 structure is purely coclosed. So this proves the first item in the Min theorem. Yes, there is a question.
Hi. Is the holonomy of this guy in SU3 then? Like, are you always getting?
Yes, indeed.
The dimension of the complement to n prime is the holonomy, dimension of the holonomy group of the resulting connection. So.
Sorry, say again.
So is it the case that the dimension of the complement to n prime, so Tor, I think you've called it, is always the dimension of the holonomy group of the resulting connection?
The dimension of the complement.
So in this case, SU3, it goes.
It's SU3, yes, but it's not always.
You're always the dimension of the complement to n prime is of the fixed subspace that would correspond to a holonomy group being a subgroup of G2.
Okay.
I'm asking, is that true? Well, okay.
No, I don't think that's true.
I don't think. I mean, if I understand correctly, you're asking if there is an equality between the dimension of the complement and the dimension of the holonomy. Is that?
Yes, that's the. Yeah.
No, that's not true. That's not true. In the other case, we had a 4-dimensional complement and 3-dimensional holonomy.
I think the point of this almost quasi-abelian approach is just to have a very concrete ansatz, so that the equations reduce to something that is somewhat easy to manage, right? So it's more of a choice of ansatz than an expectation on what holonomy should manifest itself. Okay. Right? They're not. It's just a coincidence here, because they made a simplifying choice to be able to completely understand the degrees of freedom in this almost abelian case. And that's a reasonable thing to do in general, right? In similar problems. It does not come from a holonomic consideration. It comes from a simplification in order to make the problem tractable. Yeah.
Thanks.
So, okay, so this proves the main theorem, the first point, and see if I, oops, well. Now I would just mention just the difficulty, what happens in the n prime of dimension greater than 2. So again, I restart with the Lie algebra of dimension 7, 3 form, dimension of n prime equal to 2 or 3. Remember that we cannot have more than 3. And then I take a G2 structure and I take a basis such that the 3 form is in the orthonormal form. The problem here is, okay, well, it's not a problem. Actually, it solves some problems. So G2 acts on the Stephan manifold, or let's say on pairs of orthonormal vectors in R7, transitively. So we can assume that we can take 2 vectors inside n prime that we know that we have at least 2, and use this transitivity to assume that the elements 6 and 7 of the basis are inside n prime. And the problem here is that we may have n prime of dimension 3, and we cannot control this third element on n prime or whatever. And okay, so we need to proceed, and we want to find a basis that is good for both the Lie algebra structure and the G2 form. So when we started working, there was an easy case to work with, easy, how do you say, well, in a sort of way, but it was not easy at all, but at least it was the case that we managed to work with. That is the case where the G2 structure calibrates a 3-dimensional subspace contained in the center and containing n prime. And if this holds, which is a big if this holds, then you can make the computations. Then you take this C and you take the orthogonal. C will be 3-dimensional again, and because of the form being of this standard, then this is E5, you have a 4-dimensional complement, and the differential of the 4 first elements will be 0, and the dual, here, and the differential of the last three would be 2 forms on Q, on the first 4. So here, Q is a 4-dimensional subspace, and so the lambda 2 decomposes as self-dual anti-self-dual parts. We use that. So we consider a basis of self-dual forms, and which is this one, which is this, well, we declare that base. And what we know from previous results is that the fact that phi is coclosed is that the coordinates of the differential of 5, 6, and 7 in this dual, self-dual part, so the self-dual part, we have d of the differential of 5, 6, and 7, which decomposes as self-dual plus anti-self-dual. So the self-dual part has to give you a symmetric matrix. Okay, this is something we knew. What we did to manage the G2 instanton condition is to, okay, you have a symmetric matrix, then you diagonalize it. You diagonalize this 3 by 3 matrix. This is 3 by 3 by an element in SO3, but this element is an imaginary quaternion, which allows you to actually not only change, because the problem is that if you only diagonalize the 3 by 3 matrix, you're acting only on C. But you need to act in the whole algebra by a G2 element in order to not to change the G2 structure. So this allows you to actually, well, in this diagonalization, let's say, you manage to find a new basis where phi is is kept. But now the self-dual parts of the differentials of 5, 6, and 7 are exactly a multiple of the self-dual basis that you took. Okay, And this is the simplest you can get. Notice that we have no control on the anti-self-dual part, which is non-trivial in general. So if you have this big if, you can simplify the structure, and these coefficients are simple enough, let's say, to make, I don't know, 10 pages of computations, and to solve exactly the instanton condition. So if this holds, if you have that phi calibrates this subspace, then you can prove this lemma. That nabla is a G2 instanton if and only if the dimension of n prime is 3, and, well, you have lambda is 1, you have the self-dual part, actually, the coefficients that you have are all the same, and you have this third condition, which will allow you to show the naturally reductive part, okay? But also will allow you to classify the algebra, of course. And from here, you can obtain 2 and 3 in the main theorem. So just how to remove the big if? Well, this was the big issue at some point. And, well, no, I will not say much here. If you're interested, I will just stay here. But so we did everything with this big if, but in the end, you can solve this big if. Because if n prime is of dimension 2, then it is easily solvable. If n prime is of dimension 3, then there are cases, there are G2 structures which do not calibrate any three-dimensional space C. What we prove is that if the G2 structure defines an instanton, then it has to calibrate C. It has to calibrate a subspace, well, n prime actually. So that's how we got rid of this big if. So, okay, now thank you very much. That's it.
Okay. Thank you, Viviana, for this very nice talk. Okay. Are there any questions or comments for Viviana? Hey, I wanted to ask you about this characteristic connection. Does it have parallel torsion?
In general, I don't think so. In our case, it does.
In all of your cases, it has parallel torsion. Okay.
Yes, that's how we prove that it's naturally reductive. It has parallel curvature, parallel torsion.
Okay.
Actually, yes.
Okay, very nice.
Yes.
And any other question for Viviana? No?
No,
Okay.
just real quick. Yeah, so thank you, Viviana. Just make sure everyone is aware of the workshop of the Bridges collaboration, which will be in France next year. Applications to attend are open, so everyone is super invited, and there are funds to support partially or fully participation, but they're going away fast. So if people would like to apply as soon as possible, that would be great. Week number 1 is a workshop, is a summer school for students and postdocs. Week number 2 is an international conference. So everyone is super welcome. Please come if you can. That was it. A word from our sponsor. Thank you, Adrian.
Okay. Okay, then if there are no more questions for Viviana, let's thank her again. Thank you very much, Viviana. I don't know how to put the clapping. No, that's here I found it. Yeah. Okay. Well,
Thanks everyone for being here.
thank you everyone for coming today to this session of the webinar, and we still have one more session left. The last